just give me a thumbs up, Warsaw, to let me know that you can hear this. Hopefully it's not too loud.
Sound waves strike the tympanic membrane and cause it to vibrate. Vibration of the tympanic membrane causes the three bones of the middle ear to vibrate. The footplate of the stapes vibrates in the oval window. Vibration of the footplate causes the perilymph in the scala vestibuli to vibrate, which in turn causes displacement of the basilar membrane. Short wavelengths from high-pitched sounds cause displacement of the basilar membrane near the oval window. This movement is detected by hair cells of the spiral organ, which are not visible in the animation. Long wavelengths from low-pitched sounds cause displacement of the basilar membrane far from the oval window. Again, this movement is detected by hair cells of the spiral organ, which are not visible in the animation. When the vibrations reach the perilymph in the scala tympani, they travel to the round window where they are dampened.
So we can regulate what we hear. We see that some are going to travel short distance into the cochlea, some are going to travel far, but they have to pass through this middle membrane and then kind of circle back to this round window where we have a dampening effect. Now, to actually stimulate the neurotransmitters that are going to synapse and send a signal to the cochlear nerve, we are going to have these waves bending stereocilia. So inside of each area of the ear, there's a little bit of fluid. Here they're showing us in the semicircular canals. If we look at a cross section, we have this perilymph that they mentioned, okay? And then we have the basilar membrane, and on that basilar membrane, there are little hair cells, and we also have another little layer there of lymph, endolymph, that is going over the hair cells. So the same thing happens in the cochlea and the vestibule, but we just call them different terms. Here we see the basilar membrane, we see the perilymph here, and we can see these connections of these hair cells to the cochlear nerve. As a close-up, we see that as the waves cause this fluid to push over the stereocilia, that bending causes a signal. It activates an action potential. And so this is why the hair cells in our ear are mechanoreceptors. The bending of the stereocilia by the movement of this fluid causes an action potential to travel and transmit the signal of what we hear to our brain. Now, the question is, the same thing is happening in the semicircular canals and the vestibule for balance. So why do you think, Warsaw, I'm gonna ask you because you had lab already. Why do you guys think, and don't let it just be Olivia who answers, but why do you guys think that when you spin around doing the Berenice test, Devin, I want to hear you too. I hope you're listening. When you're spinning around on that chair for the Berenice test, why does it take a moment for you to get your balance? If I stayed up here, Glenn, and just spun somebody around and around and around and around, they might get dizzy. Why does it take a moment for us to get our balance? Yes. Did you guys hear her, Warsaw?
No.
What do you guys think the answer might be then, before I tell you what she said? Why do you think it takes a moment for us to get our balance? Or why is a person's eyes still trying to adjust? What is going on with our senses if we spin and spin and spin and then stop?
Is it the fluid?
Yes, very good. So you guys are both on track. The fluid is still moving. just like if you were spinning something in a cup, if you stop shaking that cup, you can still see the fluid moving a little bit until it settles down. So if that fluid is still bending the hair cells, you may feel dizzy, you may feel like you're still moving, you know, because your body is trying to get back to equilibrium and the fluid to be still. Good. So they actually have a fundamental figure in your book that goes over the animation that we just did, and it also writes out in word terms everything that was in the video, so you can refer back to that for sound conduction. That is sound conduction. That is how we're able to receive a sound, let it vibrate through the middle ear, let it go through this fluid, cross the basilar membrane, bend those stereocilia, and spark an actual potential to go out through the nerve to the temporal, the auditory cortex, and our temporal lobe. Okay? All right. Does anybody have any question about sound conduction or the sequence of events here? Just showing us how it goes to the auditory cortex. It still has to relate to the thalamus. And remember, we said that for taste, for smell was the only sense that does not have to relay in the thalamus. So I'll just focus this a little bit more. So this is actually showing us here when we smell something from that nasal cavity up to the olfactory nerves, and then it doesn't go to the thalamus, it just goes to these different areas of the brain. Here, there are different centers for smell, some in the frontal lobe region that can help us associate with emotions and with memories. All right, any questions on sound conduction? Just note that everything deteriorates as we get older, of course. So, yes, you know that vision, you may have to get glasses as you get older if you didn't have them when you were younger. Maybe a slight loss in odor detection, maybe a small decrease in taste. The lens loses some of its flexibility. That's why you may need to get glasses, because it's harder to change the shape of that lens so we can see things that are close or far away. Even color perception. And some of these, our reflexes slow as we get older. That's why even with elderly people who are driving, their reflexes, when they see something, or their ability to react after they see or hear something, is slower. And balance may be off, right? They may tend to fall more due to instability and changes in the inner ear. Please also just keep in mind, protect your hearing, because if you are exposed to loud sounds over a long period of time, you can damage those stereocilia, okay? The spiral organ in the cochlea has those stereocilia, and if you damage them, they don't regenerate, okay? So you want to make sure that you protect your hearing, okay? All right, any questions? All right. I am going to start chapter 16. It's a short chapter. So we'll start chapter 16 and then we'll stop around 12. And on Tuesday, we will continue and wrap up chapter 16 and review for the test, okay? Your presentations will be next Thursday.
I have a question about the presentation.
Yes, go ahead.
Is like the full, like, final draft of the PowerPoint due today, or is it just like a rough draft?
Rough draft. So today is a rough draft outline. So you should have at least, some type of organization, okay? Have your slide